Good morning. Let us start a new topic and new chapter, that is the fourth chapter, governors. We have finished in the previous chapter flywheels. When we discussed the concept of flywheel, I have also discussed what is a governor and the purpose of the governor. And we said we will elaborately discuss both flywheel and governor when we come to the governors chapter when we start. Okay. Now let us recall the flywheel, which already covered, and what is its function and how a governor differs from a flywheel. We have seen a flywheel requirement is like this. If a operation or if a process in a particular engine will have a cyclic fluctuation, then we need a device called flywheel. Cyclic fluctuation, that means irrespective of the external load that comes on the engine, there is a variation in the torque output, okay, or the torque receiving or whatever it may be. So the torque variation takes place every cycle. So in those cases we require a device called flywheel. Okay, then we said a device called governor is required when you have a load variations on an engine. Okay, so let us first see how a governor is different from the flywheel. Okay, so you are aware of the fact speed variations. Okay, speed variations will happen by two ways. One is because of cyclic fluctuations and other one is load variations. So speed drop or speed hike may happen either because of the torque fluctuations, that is in cyclic fluctuation, it causes the speed variation. So those variations will take care by a device called flywheel, and we clearly discussed about the flywheel function, and we have seen various problems in applications like punching, riveting and other things. Okay, so where a flywheel will control your speed variation due to cyclic fluctuations. Now let us come to another one, which is a governor, which will take care about load fluctuation. Load fluctuation. So what is this load fluctuation? Let us take a simple example. Okay, a fan or an AC which we use in our home. So there is a fan regulator or AC controller is available to change its intensity depends upon your requirement. Suppose if it is hot summer, I need more speed for my fan, or I need more cooling effect in case of AC. So I will change the control knob so that I get the desired one. And similar, if it is winter, I don't require that much of cool atmosphere, or I don't require that much of speed of the fan. In those cases, I will control my speed regulator or the temperature regulator in my AC or fan. So this is in the similar way we can compare with the load variations on an engine. Load variations on an engine. Okay, so there is no guarantee that the engine will run always with full load. or there is no guarantee that your engine will always run with half load. But your engine is designed, your prime movers are designed such a way that they can take care of load variations from say 20% to 120%. We design it more than its capacity also to work, isn't it? So in those requirements, we need a device which will take care about these load variations and maintains a constant speed. Okay, maintains a constant speed. So that is what a governor. You can see speed variations will occur due to either cyclic fluctuations, okay, or load fluctuations. So the cyclic fluctuations are taken care by the flywheel, and what about the load fluctuations? A governor will take care about it. That is the first thing. Then coming to, so the flywheel may require or may not require in all the devices. Suppose if there is no cyclic fluctuation, then we don't require a flywheel. But a governor is an essential tool or an essential device which is badly needed for any equipment, because definitely there will be variations in the load in realistic life. That's why governor is an essential in devices, but flywheel may be optional, depends upon your process. The third and last one is flywheel operation is a continuous, and whereas governor operation is an intermittent. Flywheel operation is a continuous operation. That means, as I stated, it is a cyclic in nature. So every cycle it repeats. So it works continuously. It works continuously. Then what about governor? If there is no load fluctuation, then governor will not come into the picture in operation. Okay, so its operation is intermittent, and this flywheel operation is a continuous operation. So let me repeat, the flywheel is taking care about cyclic fluctuations to maintain constant speed, whereas the governor will take care about load fluctuations to maintain constant speed. And a flywheel may require, may not be required by an equipment, but a governor is an essential tool which will take care about load variations to maintain a constant speed. And finally, the operation of the flywheel is intermittent. Flywheel operation is a continuous, and whereas the governor operation is an intermittent operation. Okay. Now let us see how a governor operates. How a governor operates. A simple diagram is shown here with the necessary requirements to explain the process of a governor. So you can see here there is a device which we have shown is called a governor. It is a governor. So this governor, this is the governor. This is a governor. This governor, how it works and how your speed is maintained constant, let us see. So there are two arms, and the end of the arms, balls are connected which are called fly balls. And these arms are once again connected with the lower links. These are lower links. These are upper arms and these are lower links. And they are pivoted at an extension link. Okay. And let us see here. So this is an engine. This is an engine which is coupled to here. And the end of the engine, that shaft, there is a bevel gear is there. That means this is actually an output of a particular device or a particular engine which you are working with your requirements. So my objective is to maintain the speed of this engine, speed constant. This speed should be constant. So how I can maintain that speed constant? Let us see. Suppose let us assume the load has dropped. The load has dropped on the engine. When the load is dropped, then automatically the speed increases. The load is dropped, the speed increases. So when the speed here it increases, then this bevel gear increases its speed, and its mating other bevel gear also increases its speed. So this bevel gear which is connected to this spindle increases its speed. So when it increases its speed, then these flywheels will rotate with a higher velocity. When they rotate with a higher velocity, then they will be lifted. They will be lifted. So they will be lifted into upper side like this. So they will be lifted up, isn't it? So how? Because the speed has been increased here. As the speed increases here, also the speed increases. Then when it increases its speed, the flywheels will rotates with a higher speed. When it rotates with a higher speed, then they will fly up. Okay, when it flies up, then the sleeve will be lifted. So here you can see there is a sleeve. So the sleeve will be lifted. That means it keeps away, like lifting up. Then it causes what it causes? It lifts. Okay, when it lifts, so then bell crank lever. This is the lever called bell crank lever. Will operates a device called throttle. A device called throttle. So this throttle is connected to a fuel supply to the corresponding engine. This throttle is nothing but the fuel supply given to this corresponding engine. So then here this throttle will be closed like this. So when this throttle closes, then the amount of the fuel that enters into the engine to give the power will be reduced, isn't it? So as I said, load dropped. So when the load dropped, speed increased. That is, speed increased. But what I require a constant speed. So when the speed increase, then the flywheels moves up, then the bell crank lever will be closed. So when the bell crank lever is going to be closed partially, then the amount of the fuel that it enters into the working cylinder or whatever it may be, there the magnitude of the fuel is reduced, then automatically the power developed will be reduced, then the speed of this will be reduced, which maintains constant speed. Isn't it? So what I mean to say, when it increases the speed, then the sleeve will be lifted up. When the sleeve lifts up, then the throttle closes, then the amount of the fuel that it enters will be reduced. When the fuel that is reduced, then automatically the speed of this output shaft decreases, because earlier it was higher, now it was reduced, so that it maintains a constant speed. It maintains a constant speed. So vice versa also true. That means load increased, then what will happen? When the load increases, then in that case your fly balls now will be dropping down. Your fly balls will be dropping down. Then the sleeve will be pushed down. When the sleeve is pushed down, the bell crank lever opens this throttle valve more. Now the throttle valve is opened more. When the throttle valve opens more, the amount of the fuel supply increases. The amount of fuel supply increases. More and more magnitude of the fuel is supplied. When you supply more and more amount of fuel, then automatically the power produced increases, then the speed of the output shaft will be maintained constant. Okay, this is the simple working of a governor which comes under the centrifugal category. Why we call this as a centrifugal category? Because here these fly balls either lifting up or dropping down is a function of the centrifugal force. Because this shaft is revolving. When this is revolving, then automatically these arms are revolving, then these fly balls also will rotate. When they rotate under certain radius of rotation, then centrifugal force will be developed. We know the centrifugal force is mr omega square. We know the centrifugal force, formula for the centrifugal force is mr omega square. This is the centrifugal force. So what is m? Mass of the fly ball. What is r? Radius of the rotation. Omega, angular velocity. So this centrifugal force is function of mr omega. Of course m is fixed because once we select a ball, its mass is fixed. Then radius of rotation, of course, it varies. That is from the center of the ball to the center of the axis varies. And what about omega? 2 pi n by 60, and it is whole square. So with a small change of speed also centrifugal force changes enormously, because here it is a square term. It is a square term. So this is a simple basic principle of a governor. Then how we can classify the governors, and what is the difference between a centrifugal governor and inertia governor? We are mainly focusing on centrifugal governors only. Just now the one I have shown is a centrifugal governor. So what is the centrifugal governor? The centrifugal governor works on the principle of change of velocity. And that causes a centrifugal force variation, and that leads to moving the fly balls in a different locations, and which controls the speed variation. So centrifugal governor works on change of velocity. Then there is another category of the governor which is called inertia governor. This inertia governor works on rate of change of velocity. What is rate of change of velocity? Rate of change of velocity is nothing but acceleration. Okay? Of course, in inertia governor also centrifugal force comes into the picture, in addition to that, this rate of change of velocity also comes. Okay, so that is the basic difference between a centrifugal governor and inertia governor. In centrifugal governor, change of velocity is the principle to operate the governor, and whereas in the inertia governor, rate of change of velocity is the principle behind the governor design. So relatively the effectiveness of inertia governor is more. So inertia governor is more effective comparative to centrifugal governor. Okay, but the thing is, the construction point of view, these inertia governors are complex in nature and centrifugal governors are so simple. Okay, so that is the main reason for majority of governors in real life are centrifugal governors, not inertia governors. Okay, and our curriculum or our syllabus is confined to centrifugal governors only. Our discussion is mainly focused on centrifugal governor only. So I have shown here 4 types of centrifugal governors. One is called watt governor. This is the first category, watt governor. And the second one is Porter governor. The third one, Hartnell governor. And the fourth one is Wilson-Hartnell governor. Of course, we have some more governors like Harton governor, okay, then Pickering governor, these are once again additional to the above 4 governors, Harton and Pickering governor. So of course nobody are using Pickering governor nowadays because it was one of the oldest governor which was used in a device called gramophone. This is used in gramophone. I don't know how many of you are aware of a device called gramophone. See, in the earlier olden days, the audios, songs and everything are available on a magnetic disc. Okay, and the disc is placed on a device and it is rotated, and there a pointer will be continuously in contact so that the audio will be listened. So that device is called gramophone. Just like that, nowadays whatever you call the devices to listen your songs you are using, in the earlier days it was the only device to have a audio listening, that is by means of a gramophone. So that gramophone was used, this Pickering governor. Nowadays no way we have gramophones and we don't have the Pickering governor's uses. Of course, Harton governor will be similar to this category of spring control governor that we'll see. Here, the first and foremost governor is a watt governor. So this name is given watt governor because this was used during the period of steam engine operations. Steam engines, where the speeds of the engines were very, very less. So for those low speed engines, the governor which was used at that time was a watt governor. So I will show you in the subsequent discussion why this type of governor is not going to be used in nowadays. So this is a watt governor, which consists of simply like the previous sketch which we have seen. a fly balls, upper arms and lower arms, and the main spindle. And the second category of the governor is a porter governor. In case of porter governor, in addition to these fly balls, we place a dead weight at the center. We place a dead weight at the center. That is called sleeve mass. That is called sleeve mass. So that is the porter governor. Then coming to the Hartnell governor and Wilson-Hartnell governor. So in these governors, in addition to this centrifugal force, we provide a force called spring force. This is a spring force. So this is also a spring force. So usually in this Wilson-Hartnell governor type, we use 2 springs instead of 1 spring. So that means they are in parallel. 1 spring, you can imagine behind there is one more spring. Okay, so these are all comes under the centrifugal governor category. One is dead weight type. These 2 are simply dead weight type, and these are spring controlled governors. So one is dead weight type, and the second one is spring loaded. Spring loaded like Hartnell, Wilson-Hartnell, Horton, all are under that spring controlled governors. Okay, let us see first various types of watt governors and what is the nomenclature that we use in a watt governor. So here I have shown 3 models of a watt governor. Only the difference is, let me explain. In the first category of the watt governor, the upper arms are pivoted to the axis of rotation. In the first category of watt governor, the upper arms are connected to this axis of rotation, and in lower arms are connected to an extension link. Whereas in the second category, the upper arms are not directly connected to the axis of rotation. They are also connected to on the extension link, like lower, even upper arms also, like this. Coming to the third category, this upper arms are intersects on the axis of rotation and further extended, and they are pivoted like this. So the difference is, in the first case, the upper arms are directly coupled, and in the second case, these upper arms are placed the extension links, okay, and they will not intersect directly. And in the third case, the upper arms directly intersects and they are kept on the extension of this. So whether this is the category or this is the category or this is the category, whatever the type of watt governor, the nomenclature which we use the same. So what is the nomenclature I use and what are the analysis I require? Let us see. So most of the cases we get either this category or we get this category. These 2. That means upper arms are directly pivoted to the axis of rotation, or upper arms are connected to an extension links, both upper and lower. Okay. Now let us see the analysis of one of these. A simple diagram. Okay, the first one. See here, this is the fly ball. M is the mass of fly ball. M is the mass of the fly ball. Omega is the angular velocity, and R is radius of rotation. So the distance from the center of gravity of the ball to the axis of rotation is r. Then h is nothing but the distance from the center of gravity to the pivot point of the arms. Pivot point of the arms, isn't it? So the mass always produces the force on a body in the downward direction due to the gravitational force, that is mg downwards. Okay, and it is revolving with a certain velocity, that n, that is rpm, so omega. Okay, then it causes a centrifugal force mr omega square, and you are aware of it, and we are aware of it, the centrifugal force is mr omega square. This is mr omega square. Centrifugal force always acts radially outwards, that is this way. Then these upper arms are subjected to a tension T. T is the tension in arms, upper arms. Tension in upper arms. Tension in upper arms. H is called height of governor. H is called height of governor. That is the distance between center of gravity of the ball to the pivot point of the arms, upper arms. Now, these are the lower arms and they are free from the tension. Only upper arms are subjected to tension. Then let us define an angle theta. An angle theta, that is the angle made by upper arm with vertical. Theta is the angle made by upper arm with vertical. So from the geometry, if this becomes theta, then this also becomes theta. Okay, if this becomes theta, then this also becomes theta. Then take the free body diagram of this fly ball. Take the free body diagram of the fly ball. That is the free body diagram of the fly ball, like mr omega square, mg, and this is t, this is theta, of course this is also theta. So you can write the force analysis resolving in horizontal direction and vertical direction. So this is theta, okay, then t cos theta, what is it? This is t, so this is t cos theta, upward direction. T cos theta is nothing but balanced by the downward force mg. So you can see here t cos theta is equal to mg. T cos theta is equal to mg. Similar, if I resolve horizontally, then this is t sin theta. So this is towards right and this is towards left, then that is, 2 sin theta is equal to mr omega square. So t cos theta is mg, which is resolved vertically, okay, and horizontally it is t sin theta mr omega square. Then just divide equation, let me call this is 1 and this is 2. So 1 by 2. So equation 1 by equation 2. That is t sin theta by t cos theta. Okay, t get cancelled, then tan theta. So that is equal to mr omega square by mg. So here m get cancelled, then r omega square by g. R omega square by g. Then look at this diagram. Tan theta can be written in the other form. This is theta. Tan theta, opposite side by adjacent side. That is tan theta is equal to r by h. Tan theta is equal to r by h. So left hand side I have written tan theta is equal to r by h. Already right hand side I have r omega square by g. Then cancel r, then you get h is equal to g by omega square. H is equal to, this is we get 1 by h is equal to omega square by g. Then reciprocal of it, that is h is equal to g by omega square. Then omega plus I write n, that is 2 pi n by 60. Okay, so this is square means 2 pi n by 60 square. 2 pi n by 60 whole square. Then this becomes 60 by 2 pi whole square. Okay, then what is the value of g? If you write g value meter per second square, then it is 9.81. Okay, by n square. So if you simplify this, this becomes 895 newtons by Newton, n square meters, or we can also write 895 into 10 power 3 mm by n square. So instead of meter, if I want to write it in mm, so into 1000, that gives 895 into 10 power 3 by n square mm. Okay, so h. If you look at here, this equation, a beautiful outcome you can observe. The height of the governor is not function of mass of the fly ball. It is not function of the radius of the rotation, isn't it? It is only function of speed. You can see the equation h is equal to 895 by n square, where n is speed, okay, and it is the independent parameter. It is not depend on either the fly ball mass or fly ball radius of rotation, isn't it? So you can observe h is equal to 895 by n square meter, or 895 into 10 power 3, okay, by n square mm. Then why this governor is not used nowadays? Let us see. As I said, the watt governor was used in the olden days, keeping in mind their speeds were less. But now it is not used. The reason behind it can be illustrated by seeing this table. So let us take here, for various speeds, what will be the height of the governor. So what is this height actually? When the fly balls will lift up or drops down, so how much amount of the sleeve is going to be changed? The change of the sleeve is controlled by h. So here we have written an equation, h is equal to 895 into 10 power 3 by n square. That means if I put different values of n, I get a different values of h in this equation. Let me first substitute my n is equal to 50. Okay, that means 895 into 10 power 3 by 50 square, that is 2500. Then I get the value of h is 358 mm. If I put the speed is 100, then h becomes 89.5. And if I keep 150 is the speed, then this will become h 39.8. So on, 200, 300, 400. You can see the drop is how differs. Very beginning say 100 speed and 50 speed. This speed variation, like 100 to 50 speed variation is 50. 100 to 50 speed variation is 50. This 50 RPM speed variation caused the lift of the sleeve is 358 minus 89.5. That is 100 minus 50 is 50. So speed has been increased to 100 from 50. Then the height of the governor has been changed 89.5 from the beginning of 358. That means you have ample amount of lift, that is around 250. Around 250, isn't it? So, whereas if I move it to 150, the difference is how much? 100 minus 150, 100 minus 150. So, that is 50 only. But in the second spell, what is the difference? 89.5 minus 39.8. That means, let me take it as a 40, 40, that is 90, 90 minus 40, 50. Okay, here also considerable lift is there. Then come to this 200 to 150. So, for the same 50 mm of 50 RPM difference, it has been dropped to somewhere around 16 or 17 mm. What about here? Look at this. 300 to 400. What is the speed difference? 100 RPM. How much difference of the lift you got? So that is 400 minus 300 is 100. 400 minus 300, 100. RPM change. Caused how much lift change? 9.9 minus 5.6. Let me roughly 10 minus 6, 4 mm. If you have a time, you can calculate for further higher values like 500, 600, 700. So for those higher speeds, you get lift of the sleeve hardly 1 mm, half mm, still lesser values. You get the lift is half mm, 1 mm, that's it. So that small amount of lift will not control your load variations or your speed variations effectively, because even it is a small amount caused lift that may not reflect in the output because there is a friction. That friction will consume that. That friction itself will consume that. Okay? So, and if you see these RPMs, 400, 500, 600 RPM, nowadays it's a funny RPM. Even your wet grinder, your mixies, your fans, all will run with more than 2000 RPM, 1500 RPM like that. So if it runs at like 400, 300 RPM, then your mixie will not even operate to churn the buttermilk, isn't it? So the juice will not be obtained if it runs with a 400 RPM or 500 RPM. But 100 and 200 years back, so those speeds were okay. Suppose if I say now I am giving you a two-wheeler which will run with 20 kmph and the pickup is like it takes 30 seconds to reach for say speed of like 10 kilometers per hour to 20 kilometers per hour, will you buy it? No doubt you don't buy, isn't it? So because the steam engine times, the speeds were very, very less. Those speeds are enough during those days. That's why those days this governor was worked well, but nowadays this cannot be used because this RPM, 400 RPM, is literally not at all useful for any of the present devices. That is why this watt governor is studied only for the purpose of academic purpose We don't use this governor nowadays anywhere in this country. And its further modification is a Porter governor, where this problem which we have seen here, this problem can be overcome. Okay, so in the next lecture we will see the Porter governor. Okay, this is a Porter governor. By adding additional mass, okay, a dead weight is added at the center of the sleeve so that its effectiveness will be increased. So we discuss in the next lecture this effectively this part, isn't it? So what we discussed today is how a flywheel differs from a governor, and what are the classification of governors, and what is the operation of a general governor, and what a watt governor basic principle, and why watt governor is not used nowadays, and what is the limitation for a watt governor, then what is the need of going for another governor called Porter governor. This is what we have discussed today's lecture. We will continue in the next lecture for the analysis of Porter governor. Thank you.